Hello, my name is Pauline Basani. I'm going to be taking you through the project presentation for Group 15. So our project is titled A Single Model Architecture for Scalp Pathology Detection, where we use computer vision and semi-supervised learning for trichology, which is scalp and hair diagnosis. This is what we are going to follow through our presentation. So I'm going to dive into the introduction. So trichology is the dermatology branch which focuses on hair and scalp health. Traditional diagnosis relies on manual visual inspection, which is subjective, inconsistent, and time-consuming. Our solution replaces this with machine learning on image datasets, which offers standardization, objectivity, and scalability. For the background, we are looking at why our project matters. So scalp disorders affect millions globally, yet diagnosis remains dependent on specialist visual evaluation. Our project applies machine learning and image analysis to achieve objective, reproducible, and scalable trichological assessment. For the related work, you're going to look at where does our work fit, like is there something that already exists in regard to what we are working on? So prior studies show CNNs outperform manual inspection for hair disease detection. Researchers have proposed follicle classification, heat map generation, and multitask networks for several estimation. However, critical gaps remain dataset diversity, annotation quality, and the need for clinical validation. Next, you're going to look at the problem statement, which is categorized into two, where we have the domain application problem and the computational problem. So for the domain application problem, we have manual inspection being subjective, inconsistent, and time-consuming. Therefore, we need a clear, standardized, and scalable diagnosis alternative. Then for the computational problem, building robust machine learning workflows requires thorough EDA to detect biases and imbalances, which is followed by models that maintain accuracy under real-world conditions. So these models that you're training are going to work under different conditions. We need to ensure that even under these different conditions, the models are still accurate and are performing what they're expected to do. So yeah, that's for the computational problem. Next, I'm going to move to the research questions. These are some of the questions that we are trying to answer with the project that we are working on, the machine learning project. And these objectives are the answers that are generated from the questions that we have looked at in the previous slide. So first, we have to perform EDA to assess integrity, identify biases in the dataset, and prepare high-quality inputs for semi-supervised learning. Then to evaluate a semi-supervised framework against fully supervised baselines using standard metrics. Then finally, to assess clinical applicability. Under the clinical sector, where can our solution be applied? So can our models provide objective, consistent, and scalable predictions? And these are the problems that we are facing with the manual inspection. So we are trying to solve these problems using the solution that we have come up with. And then these are some of the research contributions and outputs. Our main contributions are first, a semi-supervised learning framework for early scalp pathology detection. It uses a small labeled image set, a small image dataset plus a larger unlabeled pool, and then may apply confidence-gated pseudo-learning and consistency regionalization. Then a single model architecture combining trichoscopy images and microbiome data, producing predictions that are biologically grounded. Then finally, the 20 interpretability visualizations showing dataset distributions and real-world scalp image characteristics. Then we have some of the images that were output from our EDA. So these are results from the data analysis. The horizontal bar chart shows class distribution, dandruff, where we can see that dandruff comprises 34.1% of annotations, and then followed by folliculitis, which has 12.9%, and alopecia areata with 12.8%. Then the long tail the long tail of rare classes such as psoriasis, gray hair, reveals severe class imbalance, necessitating class-weighted losses or oversampling. Then we have the imbalance is further quantified in these graphs. This chart plots the imbalance ratio, which is the majority to minority count. So dandruff has an extreme ratio of 30.7. The Pareto chart shows cumulative annotation counts. The top three classes account for over half of all annotations, and the 80% mark is reached after the four most common conditions, which are explained in the paragraph below the illustration. With the data characterized, let's discuss our models. We explored multiple architectures. For classification, we looked at Vision Transformer. Then for detection, we looked at faster RCNN and mask RCNN. We also evaluated the real-time detection, which is RT-DETR, standardized transformer, and SVM with efficient net B3 features. Subsequently, we applied modal compression, and we applied pruning, quantization, and knowledge distillation. For the results from the models, for Vision Transformer achieved the highest classification accuracy at 70.9%, with macro F1 of 0.788. It excelled on contact dermatitis and alopecia but struggled with head lice due to limited samples. So this is where the challenge of class imbalance comes in. Then YOLOv8 for detection achieved MAP at 0.5 of 33.9%, which is slightly below faster RCNNs, which is 36.3%, but YOLO offers better speed for real-time use, and contact dermatitis was most detectable. Dandruff and head lice were challenging. Then SVM with efficient net gave 64.1% accuracy but failed completely on psoriasis. Next, we are going to look at the dataset description. Returning to our dataset comes from RoboFlow annotations with additional metadata. It contains high-resolution scalp images labeled for some of the scalp conditions such as alopecia areata, folliculitis, and dandruff, and other conditions. Then also on this side we have the explanation of the EDA, which images were generated on the slide that had the results. The current status, which is the discussion, we are standardizing labels, cleaning metadata, fixing imbalance with augmentation, and running trial pipelines before full training. One of the challenges we are faced with our datasets is class imbalance, so we are trying to see how to apply class weights to try to solve the problem of class imbalance. Then our 4 next steps include cleaning metadata, fixing the imbalance, normalizing data loaders, and running baseline trials. Some of the limitations that we faced. Some of the limitations that we faced included few labeled images, dataset imbalance, pseudo labels may add noise, and results are research only, which needs real clinical validation. In conclusion, semi-supervised learning helps with limited data, and single model architecture combining images and microbiome works. We improve early detection and show ways to reduce bias. These are the acknowledgements, some of the sources that we got our data, which is RoboFlow, and some of the collaborative tools and platforms that we used for assignments like Kaggle. Thank you.